Alright, we've got an NMR IR combo. Again, I've tried to replicate the NMR and IR as best I can from my originals. But I'll describe it, and of course as you do your own examples, you'll get familiar to what these kind of diagrams look like when you actually see real things. We've got C4H6O2 here. Let's take a look at the IR first, okay? Here's the 3000 mark going here. All of my peaks are to the right or lower than 3000. So I'm not dealing with any carbon-carbon double or triple bonds here. These are all alkanes. So this tells me I have alkanes that I'm messing with. I also don't have, I'm not above 3000. So I have this monstrous peak on my spectra that's right here. This means I'm dealing with a carbonyl. Okay? So I've got a carbonyl because of that peak right here. And really below like 1800, I don't really care what the other stuff is. Again, if you're an expert or you're learning this in your class, that's totally fine, but I usually don't deal with those. They haven't been too helpful for me. Now, notice I have two oxygens. I guess I could have two carbonyls, but it's more likely I'd have like a carboxylic or an ester or something like that. Okay, so I'm pretty much thinking something like that. If this were fully saturated, it'd be C4. It can't be fully saturated because I got the double bond, and it's 2n plus 2. So 2 times 4 is 8, 9, 10. Again, if you want to take a look at my degrees of unsaturation videos, you can see how this works. But 10 minus 4, 10 minus 6, you subtract the number of hydrogens, you get 4, and you divide that number by 2, that's the degrees of unsaturation, or the number of rings and double bonds. One of these double bonds is coming from right here, so I either have another double bond in my structure or a ring, but I'm going to rule out the other double bonds because I don't have alkenes. So I have a ring. I have to have a ring. It's not an aromatic because I know I don't have other double bonds. I have 2 degrees of unsaturation, and so that first degree is here. The second degree can't be from another double bond because the IR doesn't show that. It has to be a ring. So I'm working with a ring here. So it looks like one member of the ring is probably the oxygen, and the other 4 members of the ring are these 4 carbons here. So I think, just from the IR, I think I'm dealing with this. Okay? Because that would give you 2 degrees of unsaturation. It'll explain why all the carbons are alkanes. And it would put in both oxygens for me. It explains the carbonyl. It's pretty nice. So I'm actually dealing with the ester here that's in the ring shape. Okay, I didn't even get to the IR, the NMR yet, and I think I have the answer. Okay, so integration here is 2, 2, 2. 2 plus 2 plus 2 is 6, so it actually sums up to the number of total hydrogens. It looks like I have a triplet in the first scenario, and then a triplet, and then some mess. And on the original, that last one is a little messy. So, if I have 2 triplets, let's take a look at this. Triplets means I'm next to CH2s. So this is next to a CH2, and that's next to a CH2. And this is probably the CH2 that's next to these other 2. So, for example, in this diagram, or what I think the molecule is, okay, so I think it's this. Let's just confirm this with the NMR before I'm really sure. This would give a 1, 2, plus 1, 3 triplet. This one would give a 1, 2, plus 1 triplet. And this one would give 1, 2, 3, 4, plus 1, a quintet, or really a multiplet. Sometimes after you get above 4, it's hard to recognize the quintets or sextets, etc. So this would fit nicely, and if I label these A, B, and C, A is most likely this one right here, because it's right next to the oxygen. And oxygen will bump you up between 3 and 4, okay, for your peak, and that's at 4. B is most likely this one. It's kind of close to a double bond, and so it's a higher end of the alkane range of 2. And so I think that's B, and I think C is this one, because it's the furthest away from anything, it gives the lowest shift, and it's the multiplet. So I think this is a structure right here.